Welcome to the people who have joined us. We have Anton Cherepanov and Robert Lipovsky from ESET talking about Industroyer. Gentlemen.
Thank you. Hi all. So I'd like to begin by saying that it's a great honor and privilege to be standing on the stage of Virus Bulletin conference again. I think it's the 5th time for Anton, 7th time for me. And if I go back and think about all the topics which we presented, each and every year the topic was more sophisticated, the attack was more sophisticated than the previous year. So I'm already kind of dreading what's going to be the next big thing that we're going to submit for VB 2018. But today we're talking about Industroyer. It's also privilege, something which we usually take for granted, but the lights are on here, the projector is working, which is great, because Industroyer is a piece of malware which can cause a blackout. In fact, it already caused a blackout in Ukraine last December. So it's a piece of malware which can do something like this, but it's the first malware specifically designed to cause a blackout, to attack power grids automatically. And for that reason, we consider it to be the biggest threat against industrial control systems since Stuxnet. Let's put this malware into the context of the other previously known malware families which were used against ICS attacks. And this is how such an attack typically unfolds. So you have an industrial site which can be anything from a uranium enrichment plant through an automobile factory, a manufacturing plant, anything. It's got its specific tailored ICS hardware, and these devices, they're typically controlled and monitored through workstations, typically running Windows, and with human operators sitting behind them. And that was the point of infiltration in all the previously known malware cases. That's where the attacker got in, and through that they got access to the rest of the ICS environment. Now, the individual families, they differ in the methods and their capability of interfering with the ICS process. With Industroyer, it was, as I said, specifically designed to attack power grids. So it was a electricity distribution substation, or distribution or transmission in the last case, which was targeted. So the commands which were being sent from the malware to these devices were tied to a timer which was built into the malware that would activate its malicious payloads, open circuit breakers, and stop the flow of electricity. So that's the high-level overview of the threat. Now, with this capability, Industroyer joined this elite club of only 3 previously known malware families, which were to our knowledge, to the knowledge of the industry, used in ICS attacks. So Stuxnet, of course, needs no introduction, right? It was able to reprogram PLCs to change the rotation speed of centrifuges. Havix, the malware also known as Dragonfly or the Operation Energetic Bear, mostly active around 2014, used to target several industrial sites. It's interesting that this malware was also abusing the OPCDA protocol, something which Industroyer is also abusing. But unlike Industroyer, Havix was only using it for espionage in a reconnaissance phase of an attack. It didn't actually interfere with industrial hardware as far as we know. Now, Symantec recently published research about new Dragonfly campaigns, so I recommend you read that as well. It's probably not the last we heard from this group. Now, BlackEnergy is a little bit different from all these 3 other malware families in that it wasn't designed, it wasn't specifically created to attack ICS environments. Instead, it's a more general purpose cyber weapon. We've been monitoring this malware for quite a while now, and we've already talked about it at VB twice. So I won't get into too much details. We monitor the evolution of the threat. And we watched all the campaigns unfolding. They were mostly being spread through spear phishing campaigns. We even discovered a 0-day in PowerPoint that it was using at one time. And over all those years, there were many interesting targets, many interesting campaigns, again, many interesting targets, which were often high-value targets. So there was government, news media, critical infrastructure, transportation, and so on. But what's relevant to our topic today, of course, is what happened on December 23rd of 2015, which was the culmination of the attack that used BlackEnergy against the Ukrainian power grid. That was the first time in history where malware was used and aided a blackout. Now, as I already said, BlackEnergy is a bit different. So from the other ones, it's general purpose. It's a modular piece of malware. You can see some examples of plugins or modules which we detected and analyzed. So there are reconnaissance modules and things like that. It doesn't have the direct control, the ability to directly control the ICS. So what they did was they only used BlackEnergy as a vessel of gaining access to the network of the Oblenergos, the electricity distribution substations in Ukraine. And then they used legitimately used remote access software called Radmin, and then connected remotely, and then manually had to click on buttons and open circuit breakers. So in case you didn't see this video, this is a video taken by one of the operators sitting behind that workstation at that afternoon, trying to document, look, somebody's remotely accessing my system, opening circuit breakers, the mouse is moving, and it's not me touching the mouse or the keyboard. So that's the actual SCADA software used to control the substation. Okay, but let's move on to the main topic of today, and that's Industroyer. On December 17, 2016, notice that's almost exactly 1 year after the previous blackout, so we were struck with a sense of deja vu because there was another one. Shortly after, we got our hands on samples, which quickly became the main suspect. Those were the Industroyer samples. We analyzed them. We provided our analysis back over to Ukraine sometime after, but we were not able to go public with these findings until June in order not to interfere with ongoing investigations. So I've already shown you what Industroyer is capable of doing and what it did. But we can take a look at under the hood how exactly it goes about doing that. So the control flow, the execution of the malware begins with a main backdoor. It's not particularly interesting. It's the kind of malware all of us analyze hundreds or thousands every day. These are the commands that it supports. Perhaps the interesting one is the last one. In order to install itself, to get persistence, replaces the image path registry value of a specified service and points it to a copy of or a more obfuscated version of itself that it drops onto the system. So the main backdoor, it also executes a couple of other modules. So you can think of all these components as, let's call them supportive or auxiliary modules. Only a couple of them are worth mentioning. For example, there's an additional backdoor, the purpose of which is a backup mechanism. So in case something happens to the main backdoor, they want to make sure that they stay in case the first one gets detected or disabled. It masquerades as it's basically a Trojanized version of the Windows Notepad application, and it's a fully functional version of Windows Notepad, which it's able to replace in the system since it's running with admin rights. A couple of other modules. There's a port scanner, which they chose to implement by themselves instead of using the readily available Nmap, for example. There's a denial of service tool, which is interesting, but I'll get to that in a later slide because that actually directly interferes with the ICS operation. Now, here's a bit of detail which was previously unpublished. So the attackers, they got their hands on on this software that's used in Ukraine. It's an in-house, custom-built piece of software used at substations for collecting logs. It has maps of the environments and stuff like that. You can see some screenshots of this software over here. And they reverse engineer this software. It was previously not known to them that something like this existed. And they found out that it's using a database to store all this information, and the credentials to that MS SQL database were hard-coded within the binary. So, okay, that's a weakness that the attackers could abuse, and they did. So they chose to execute some of their shell commands during the first reconnaissance phase of the attack through this database, through a functionality called XPCMD shell, which they first had to enable. And then they were able to run arbitrary shell commands on behalf, in the context of the database. Now, this brings obvious advantages of stealth, so it's less suspicious that these commands are being executed. And also, since they stored some of the malicious binaries within the database itself, they were also able to use it as a mechanism of evading AV detection. But now we're getting to the really interesting part, which is one of the payloads. The payload modules of Industroyer are launched by a launcher component. But before we talk about the payloads, let's categorize them. So there were three distinct types of ways that Industroyer is able to interfere with the operations of an electricity distribution substation. One of them, the first and the most important one, is directly controlling opening circuit breakers through by directly talking to these devices. Now, you may be asking, so what are these devices I keep on talking about all the time? So here are two examples from two different vendors, which are used typically in Europe, Siemens and ABB. So these are, without going to electrical engineering 101, these are so-called intelligent electronic devices, typically protection relays. Their purpose is to balance the power grid, protect the environment from power surges and so on. Now, these devices, as I mentioned in the introduction, they're controlled and operated by humans sitting behind Windows workstations. And they configure them through specialized SCADA software. Two examples for you are shown over here. Now remember this software because it's going to be important towards the end of our presentation. And the communication between those controlling workstations and the devices themselves, it happens through one of there are several possible industrial communication protocols that can be used. Some of them are regionally specific, some of them operate through serial connections, some of them over TCP. It's not really that important, but the overall idea is the same, to to send commands to these devices. Now, what's important to note is that Industroyer abuses these protocols. It's able to speak for, which Anton will describe in more detail, but it doesn't involve any exploits. It doesn't involve any software vulnerabilities per se. It's abusing the protocols in the way that they were designed to be used, but they were designed decades ago without security in mind, particularly. So now I hand the microphone over to Anton, who will guide you through the analysis of the payload.
So that was me. So Robert mentioned the exact timing of Industroyer attack. That's a job of the launcher component. The launcher samples we analyzed would launch the payload models on December 17, so shortly before power outage, so it has hard-coded time. We identified models capable of controlling devices through 4 communication protocols: IEC 101, IEC 104, 61850, and or PCDA. Most of them are DLLs with their own configuration files. First, 101, it requires a configuration file. Here is an example of such configuration. It communicates over serial connection. So attackers should define COM modules in configuration. And first thing it does, it kills a legitimate process on workstation responsible for controlling the device and takes over. The device operates on something that called IOA, information object address. Think about them as network port or registers. There are several types of IOA, but payload is interesting only in two specific ones that can accept commands. It goes over range of IOAs defined in this range of IOA, it defined in configuration, and it sends command sequence at first off, then on, and then off again. The idea behind 101 or 104 payload is very similar to 101 in that sense that it sends on or off commands to the devices, but there are a few differences. It works over TCP/IP instead of COM. It has many more configuration options. As you can see here, it's possible to specify multiple station entries with different IP addresses, and it will connect to them in parallel. There are three modes of operation. Here is in configuration, we can define mode. Possible modes are range, shift, and sequence. Both for 101 and 104, attackers, they don't know the types of IOAs that are available, so they have to do some kind of brute force to find out which will accept these commands. And range and shift is used to discover IOAs, and sequence is used once they are known. Payload constructs these packets on the fly. Thankfully to Wireshark, we can dissect them. And as you can see here, this is an example of single command type IOA on number 10. The payload can write to the console, so attackers can see real time what's going on. Also, it supports console, not only console output, but also logging. This example demonstrates capability of the payload. It tries to switch circuit breakers to on or off in infinite loop, and the exact logic depends on configuration, either on or off continuously, or flipping back and forth between iterations. 61850 is a bit different and a bit more advanced. Like 104, it operates over TCP/IP, but the thing is that it functions even if IP address is not defined in configuration. It has auto-discovery features, so it can discover these devices in the network. It does not operate on IOA, but it operates on named elements. It looks for these hard-coded names, and they correspond to circuit breakers and switches. So it's different approach, but same purpose, to open or close circuit breakers. The last payload is a step above the rest. It's not more advanced, but it operates on a higher software abstraction level. Technically, OPC data access can be built on top of 101, 104, or 61850, or even Modbus. It uses distributed COM to discover all running OPC servers in the network, obtains named items, and it searches for these specific tags. Then it writes byte value 1 to items with these tags. But what does it mean? Let's use this tool by IBB to map the tag to actual command meaning. As you can see here, ctl open off is a breaking open execute command. So again, same purpose, opening circuit breakers. Analyzing Industroyer payloads is a piece of cake for skilled reverse engineers because they're not obfuscated or no any anti-reversing mechanism put in place, but the only thing that can and will slow down your research is annoying COM stuff. So to help analyze any future malware that would use OPCDA, we released this IDA Python script, and it's available. You can check it. So what it does, here is a screenshot from IDA Pro. Here, how it looks before the script, and here, how it looks after. Robert?
So I think all the reverse engineers in the room can agree that this is much better. So, yeah, so 4 different payloads doing more or less the same thing. It appears that the authors of the malware, they really wanted to make sure that they get those circuit breakers open. So obviously, what is the impact? So de-energizing a substation is pretty obvious, and it actually happened. We can also speculate that perhaps they wanted to do something more because they could have used a much less sophisticated piece of malware just to cause a blackout, as we witnessed in 2015. If you remember the Aurora generator test back in 2007, it demonstrated how out-of-sync opening and closing of circuit breakers could lead to actual physical destruction of an equipment. So if you didn't see that, I recommend going to YouTube, searching for that video of diesel generator blowing up itself. It's pretty interesting. Okay, so that was the first and most important type of payload functionality, but the second type of functionality, which directly affects the ICS environment, is a denial of service attack caused by that DOS module that I've shown earlier. And its purpose is rendering protection relays irresponsive. It does so by exploiting this vulnerability in Siemens cProtect devices, so it's specific to this one vendor. That vulnerability is described in this ICS cert advisory. And the way it works is that the module sends specifically crafted UDP packets to port 50,000. So knocking these devices out serves to amplify the impact of the payloads, which Anton talked about. Now, Siemens did patch this vulnerability in a firmware update, but you can probably imagine how often these devices actually get updated. And the third and final type of payload functionality discovered in Industroyer is the data wiper module. And its purpose is to make recovery after the attack a lot more difficult. It goes not after the devices, the IECs, intelligent electronic IDs, intelligent electronic devices, but after the workstations used to configure them. It's launched by the launcher component, again, depending on the particular sample, either 1 or 2 hours after the payload modules were executed. And it goes after files with these extensions. Now, if you remember those 2 examples of SCADA software that I showed you earlier, it's going after configuration files of these kinds of applications. So it will clear, overwrite, wipe out the configs of SCADA software. Furthermore, it will render the machine unbootable by corrupting its registry, and finally, it will crash it by killing all, including system processes. So, what's going on from the perspective of an operator working at a substation? So you have your protection, your circuit breakers continuously being reopened. the substation is being de-energized, your protection relays are not responding, and if you go and sit down and try to fix the problem, you find that your SCADA software is gone. So, not the best scenario for someone like that, and it's also another demonstration of the importance of backups, offline backups. So let's finish off with a couple of takeaways. As you've seen, as we've shown, Industroyer's capabilities are rather versatile. It was the cause of the last Ukrainian blackout, but it's also really configurable and can really easily be repurposed to attack power grids. And it's not just limited to the Ukraine. In other words, this attack could happen anywhere in the world. It's a scalable and dangerous threat against ICS, as we've said, the biggest since Stuxnet. But the gist of the threat is not just in the malware itself, but the skill set and dedication of the malware operator. It's not just about coding the malware, but it's in their ability, which they demonstrated in Ukraine, to become familiar with the architecture of the industrial site that they want to target. So what devices there are, what commands to send to these devices, and what will happen as a result, because this is not the typical scenario that typical malware writers are used to. And finally, the blackout which occurred last December, it hit it was a transmission facility, unlike in 2015 where they hit electricity distribution facilities. But it was one electricity transmission facility in the north of Kiev. So the scale of the impact was pretty large. This transmission facility produces more power output than all of the distribution energo companies in the 2015 attack combined. But the duration of the attack wasn't, it didn't take that long. The lights weren't out for that long, which is kudos to the Ukrainians that they were able to recover so quickly. It lasted about 1 hour. But the point I'm trying to make is that if you have a piece of malware, a cyber weapon with capabilities as we've demonstrated, a blackout of 1 hour around midnight is probably not the worst you can do, right? So it begs the question, what happened? Why was that? Either they were not 100% successful in their attack, or another hypothesis, which is what we believe, is that it was not just a demonstration of their abilities, but also a test. They could be planning something more. So let's keep our eyes open, and thank you for your attention.